everyone, how are you doing? I am still playing the video in the background. I was like, what's that music? What's that noise? It is the video in the background. But hope everyone's doing good. Just sent out the announcement about office hours. Going to start doing data analytics here. A lot of people have asked for it, so I figured that'd be a good help to you. But who's in the chat? Ubot's awake right there. Let's put a note here, data analytics. Stat 201, data analytics 3. Go over to the assignments and get it going. So the key to these is writing good interpretations. Skylar, good to see you. Let's throw you a first 100 points of the day right here. 100 points, Skylar. And we're going to data analytics first. A lot of people have asked me about that. It's due tomorrow. So we got that. Okay, let's head over. Check it out. So here is the data analytics assignment for this semester. Really good assignment, understanding mosaic plots and contingency tables. Now, I want you to know I've got video help posted here. I do slightly different material, and make sure to follow the what. Can I hear it in the chat for 50 points? Whenever you are doing these, make sure to look at the what to see if you're doing them properly. Like a random sample was taken. Write-up includes numeric information, the rubric right there. Look at the rubric every time. Look at what it says you need to be doing for each section. If the graders don't click the button or don't properly assign you points, let me know. So the rubric is step-by-step how you're graded. So if you're ever like, why did I get points off? You should see a thing on the rubric that explains why you're graded that way. It's made grading a lot easier. And we're going to talk about what you need, like write-up describing the nature of the relationship between the two variables, including numeric information supported the relationship. We're going to be doing that right here. Also, your information at the top. 1 point for just putting your info. I would just copy-paste this right here and fill it out. Put that at the top of your assignment. Okay, so first thing we're doing is we're making mosaic plots. Get some data up. Now, use your data. Use your data. And let me pull up that. Where's the Pokemon data set? Pokemon. On the exam, how strict are you with rounding? If you think we took off points unnecessarily, let us know. We give points back. There's usually a plus or minus 0.1, but if you feel like the grade was not correct, just let us know. Be like, hey, Brian, I think the grade was wrong. Okay, I'll check it out. Thank you, Scott, for asking. So I got Pokemon data right here. And to make a mosaic plot, what do you need? We're doing mosaic plots right now. Let me mark that. To make a mosaic plot, what do you need? Think about what you need to make a mosaic plot. Anyone know? Oh yeah, we'll do it next, Savannah. You got it. Canvas content next. Let me put it down here. Canvas content next. Canvas content 3. You got it. What do you need to make a mosaic plot? Does anyone know in the chat? What do you need to make a mosaic plot? Very good questions to understand and know. See if anyone knows. We'll go to another 10 seconds for some points if anyone gets it. I'm out of my quest bars. Empty. I'm okay. Mosaic plots. What do we need to make a mosaic plot? What do we need? Any ideas? Like what variables? What kind? Do we need 1 variable, 2 variables? What kind of variables make a mosaic plot? Hints are on the screen currently. Here's a hint on the screen. We need axes. We do need axes. We need 2 variables. What kind of variables do we need? And you can see it down here in the corner. We need a bivariate combination of what variables. We're going to make some mosaic plots here. 2 categorical variables. Savannah, 100 points right there. I'm hitting wrong buttons everywhere. So here we go. 2 categorical variables. I got built our barbells. You want to switch it up? Side note. Built protein bars. I don't even know what barbell protein bars are. Okay, so we need to take a random sample. You'll take a random sample for yours. Tables, subset to take a random sample. 400 plus the last 2 of your UTID. So make sure you follow the instructions if there's the future or anything. Look at what yours says. Mine, I think, says this semester 400 plus the last 2. Table, subset, and then go here and take like 4. Don't take 400. Take 400 plus the last 2 of your UTID. You can actually click OK at this point. Oh, you can't anymore? What? Oh, you have to hit enter. That's the way to do it. You go here and you type 400 and then you hit enter. Oh, man, they changed it. Okay, you got to click the button now. Table, subset, random subset, 401, 400 plus the last 2. Like if the last 2 of yours is 01, do that. And now in the corner, you see 401. You've done it properly. You have your random sample. Make sure you take a random sample. That's part of your grading right here. So as you can see right here, one of the first things you'll see is was a random sample taken, and it says here take a random sample of 400 plus last 2 of your UTID. Yeah, no worries. Yeah, we'll be doing it here in a moment. Thank you, Savannah. Those are good. Happy Valentine's Day, Andrew. 50 points for everybody. Happy Valentine's Day. Hope you're doing well. Happy Valentine's Day. Give my wife some chocolate this morning. Yay, chocolate. So next we're going to create a contingency table. This is the variables you'll be using up here. You're going to include in it or remove the total and column percentages. Andrew Wind is the best. So we're going to go right here and we're going to remove the total and column percentages. So let's show how to do this graphically. We're going to go here to our data. I'm going to go to analyze fit y by x. I'm going to analyze legendary and see if legendary, we got type right here. Does type explain if something is legendary? So does the type of Pokemon is primary type explain if it's legendary? And if you notice, it's a bit of a crazy graphic, but a lot of the legendaries are dragon Pokemon, and 38 of, yeah, well, no, it does. So there might be some relationship, and the relationship, oof, this table is so large. Oof, oof, oof. Well, you know what I'm gonna do? Don't take as small as a sample as I'm taking. Don't do this. Don't do this. Okay. Don't do that. Analyze fit y by x. Does type explain legendary? I'm gonna reverse it. I just want you to be able to see the graphic. Does legendary explain its type? Okay. The table is viewable now. Your table will not be as crazy as mine. If you notice, still the legendaries are only made up of this very small sample of psychic, water, and ghost. So notice right here, if it is a legendary, there's a 33% probability it's a ghost type. If it is a psychic, there's a if it is legendary, excuse me, given it is legendary, conditional distribution, the probability it is legendary, or oh my gosh, I can't even speak. Given it is legendary, the probability it is psychic is 33%. Given it is legendary, the probability is water is 33%. Given it is not legendary, the probability it is bug is 15.38%. This is conditional not legendary. This is conditional legendary. Now what we're going to do is we're going to click the red arrow right here. We're going to remove the total percent, and we're going to remove the column percent, just so you can see exactly what I did right here. You click the red arrow right here, and you get the drop-down menu. It should only have this. Kayla, good to see you. Oh, yes, thank you. Oh, I bet you're doing great in law school. Kayla, so much. Oh, thank you. It's the married life, I guess, right? Kayla, we're hitting we got Andrew Wind and Kayla here. This makes my day. Are you at law school at UT again? I remember you saying you're doing law school, and congratulations on that. So awesome. And been married, there's Smokey in there. I got a picture of my wife right here. There's Smokey. I don't show her on stream, but I got the picture right here of my wife, and Valentine's Day. So if you ever want to swing by, say hey. It's so good, and I'm honored. The students just, man, Kayla, we had like 3 Kaylas one semester. So like 2.5 years ago right now, right? Oh my gosh. Feels like forever ago. And so thank you for swinging by. It's, oh my gosh. Kayla B, Kayla G, so many Kaylas. Love it. And right here, we have the data on if Pokemon's type is associated with legendary. So with this, let's think about what we have right here. In this table right here are the conditional distributions for if it is legendary, the probability it's ghost is 33, the probability it is psychic is 33, the probability is water is 33. And you'll notice that are the percentages right there. Here's all the percentages for the not legendary. If it's not legendary, the probability of this, yay, thank you so much, Kayla. And these are all the probabilities here. This is kind of more evenly distributed among the not legendaries on the types they are. And I had to make this smaller so you could see it, because this is what you will be screenshotting. You will be screenshotting both of these right here. So you need to come in here and get your mosaic plot on your table. Now I want you to think about what you're writing up. And we see this elsewhere. We saw it in the big plot too. Just think about the relationship, even if we go to the full data set. If you know anything about Pokemon, we'll do type and legendary here like this. If you notice, If it is dragon, it is more likely legendary. It's just like it's like, what's the least likely to be legendary? Bug. I don't even, is there even one bug legendary Pokemon? There is apparently, with all these Pokemon, there's no bug type 1 legendary Pokemon. You say, I got a bug Pokemon, but that's not legendary. So there is an association between these two variables, because knowing the type it is would give you information about if it's legendary, or knowing if it's legendary would give you information about the type it is. So the X variable, whichever one you put as the X, is going to be the one right here. Like, knowing it's legendary gives you information about what type of Pokemon it is. Given that it's legendary, the probability that it is bug type from this data, or ghost type from this data set, is 33%. Given it's legendary from this data set, the probability it's psychic is this. Given it is a legendary, the probability it's water is this. Notice how these differ greatly. If it's legendary, it's much more likely to be a certain type than if it's not legendary. And these are the percentages you need to quote. You need to compare these. You need to say, like, you know, ghost, there's not even a single, in my small data set, there's not a not legendary ghost. There's none of those. All the Pokemon in my data set that were ghost were actually legendary. 33% of the legendaries were ghost. Meanwhile, of the non-legendary, 0 were ghost. 0%, also 0. Notice how we're quoting numbers and backing it. The more different these are, the stronger the association. So the more difference is in the conditional distributions, and check back on chapter 3 for this. The more differences in the conditional distributions, like this right here is a difference. You notice how the blue, and I can't even find the little, oh, because it doesn't exist. That is 0 over here. It doesn't even exist. So there's big differences. Now, if you have no differences or a weaker relationship, then the conditional distributions will look more like that. It won't look, it doesn't have to look perfect, but it will look more like this. So that's a one you'll probably see. If it's weaker, this is exactly no relationship. And the stronger the relationship, the bigger the differences in the conditional distribution. So understand what you're looking at here, understand what the numbers mean, be able to quote the numbers in the output and compare them and talk about whether you think there's an association relationship or not. Huge thing to note, this is not correlation. Correlation is only between two quantitative variables. Do not call this correlation. I take off points when students do that, as I think the graders should. So that's how to do the mosaic plot. Let's just quickly look, make sure we have everything from the rubric. We took a random sample, make sure to do that. Proper screenshot, make sure to not get any extra backgrounds. Don't get your toolbar, don't get the top of the window. Look at my screenshot here again. You can see I only got the parts that we're talking about, the mosaic plot, the contingency table. Only get those. You can crop it if you take extra. You can click the picture, click picture format, and click crop, and just drag in the window. Make sure it looks nice and pretty right there. Write-up includes the relationship right there, including numeric backing. So we talked about the conditional distributions, like given it is legendary, the probability it's a ghost was this. Given it's not legendary, the probability it's a ghost is this. We see big differences in this, giving evidence of an association. Bigger the differences, more evidence of association. Smaller differences, less evidence of association. Now we go to the side-by-side box plots. Does anyone know in the chat for 100 points, what kind of variables make side-by-side box plots, as I take the note right here? What kind of variables make side-by-side box plots? Does anyone know what kind of variables make side-by-side box plots? Don't know? What kind of variables make side? This is good stuff for the test. What kind of variables make side-by-side box plots? It's down here in the bottom corner. Cat and quant. Savannah getting all the points right there. Cat and quant right there. Categorical X, quantitative Y. And that's box plots plural. A singular box plot's just quantitative. A bivariate display where you have multiple things being shown to you is going to be categorical quantitative. Now, legendary Pokemon are the most awesome Pokemon. Everyone knows that. So we're going to look at legendary Pokemon again right here. And we need to have our random sample. I think it's 400 again. No, this time it's 123. So be careful. Take the proper sample size. So we're going to go here to our data. We're going to go to analyze tables. Yeah. That's what we're going to do right after this. We're going to go over Canvas content right after this. You got it, Skylar. Thank you, Skylar. And we're going to go to tables, and then we're going to go to subset. We're going to click the random sample size and 100 plus the last two of your UTIDs. So these will be whatever the last two are. So you have 100 something, and click OK. Make sure it looks just like this right here, but the last two of your UTID. Now that we have 100 plus the last two of your UTID, oh yeah, we'll do that too, Skylar. Name a question. We'll start doing it right after this, or after Canvas content. So here is our random sample of 101. 151 was the original. And so now let's go right here and go to Analyze Fit Y by X. With Analyze Fit Y by X, we are going to go to Legendary as the X. You'll use your variables. Notice how it's red, which means categorical. And then we're going to go to how fast they are. How fast are these? So we're going to compare the speed of legendary and non-legendary Pokemon. The way I like to read this is does legendary explain why a Pokemon has a certain speed? Does legendary explain why Pokemon has a certain speed? Once again, this will give us side-by-side box plots because the X variable is categorical, the Y variable is quantitative. Jump even shows you this in the bottom corner, how the pairing of variables creates certain outputs. Alexander, good to see you here. We're on Data Analytics 3. We're talking about side-by-side box plots right now. Notice how we get right here, this says one way because this is the X is the red and the Y is blue. So you get, it says one way, it's a one-way ANOVA, but you're doing side-by-side box plots. There's regression, there's logistic regression, and there's a mosaic plot. So it's very similar to what I've drawn on the graphic over here. I have the names of it, like the logistic regression is quantitative Y, categorical X, and that's where logistic is. So quantitative Y, categorical X. We don't do logistic in this class though, so they even show you the combinations of what you'll get down there. So now we're going to click OK. Make sure to have your variables here and your random sample size. We click OK, and you notice there's a lot less legendaries, but let's go here. Oh, I love that question. You got it. We're going to click the top right arrow, and we're going to go to quantiles. So the quantiles are the quartiles, kind of. I think it does add extra ones. We'll see in a second. But the quantiles represent percentiles in the data. Quartiles represent like 0, 25, 50, 75, 100, like quarters. Quantiles, yeah, they do the 10% and 90%. So the quantiles are going to be the 5-number summary plus a little extra. A little extra here right now is the 10% and 90%, because those are not the extremes. Well, they're towards the end, but they're not the most extreme. So notice we have the 5-number summaries down below. Now, instantly, what do you notice about the speed of legendary Pokemon, like the center of it? What do you notice? What's some things to notice about the speeds of legendary Pokemon? Wow, actually, there's a lot to notice here. Actually, it's pretty interesting. This is I think this is actually, it's more interesting than I thought it would be, and I didn't even realize this. I'd love to do the full data set, but with this data set, there's a lot to be said right here. Think about the slowest legendary Pokemon. The slowest legendary Pokemon from this data set has a speed of 85. So that's, if it's legendary, that's the one right there. We can read which one it is. It's that one right there. That's Articuno. Articuno is the slowest legendary Pokemon. And with that, Articuno is still faster, or as fast as 75% of the non-legendaries. The slowest from this data set, non-legendary Pokemon, is still among the fastest. It's in the top 25% of fastest if it was non-legendary. We look at the medians right here and compare medians, a measure of center when data has outliers or skew, and there is some outliers and a little bit of skew to this data, it looks like. A little bit of right skew because the top, the Q3 to the max is pulled out a little bit more. So this is maybe a little right skew. Histograms are going to be better because box plots hide important features. Box plots hide important features. You should know that for the test. With this, the medians can be compared very easily, and there's a difference of 35. Notice how I'm quoting the differences. Does everyone hear me mention the numbers as I'm talking through this write-up? The median legendary Pokemon had a speed of 95. The non-legendary Pokemons had a median of 60. This is a difference of 35, which is rather large when you consider it's almost 50 or beyond 50% larger, or 50% more speed. The maximums, actually, the non-legendary had the highest, where the legendaries were a little bit lower, but the minimum of legendaries was higher than, or as high as 75% of the non-legendaries. With this in mind, we can also analyze the spread. Now, which of these has less spread? I just want you to think visually right here. Just look visually at this. Which of these has less spread? Legendary or non-legendary? Which of these has less spread? Which of these has less spread? Because there's two metrics you could compare for spread. Think of the two metrics you can compare. There's a third, standard deviation, but we're not using it right now because we're looking at box plots. So what would be the two metrics of spread to talk about and compare and contrast numerically? Any ideas? I can show you a trick. The two metrics, if you know them, what are the two metrics of spread Boxplots will show us for spread? Boxplots show us the medians. You can see here clearly that the median for legendary is higher. What are the two metrics of spread that can be viewed in a box plot? So here's one of them. I'm going to start highlighting. This is one of them for the first group. Here's one of them for the second group. Here's the other one. Notice how it's like a distance. Spread is like how far apart are things. So center is the middle. It's going to be mean or median. Median because we're using box plots. Spread is three quantities we generally talk about. There's other ones like variance. But we talk about standard deviation. Then we talk about a distance from the min to the max. And then we talk about Q1 to Q3 distance. The two metrics that can be seen in a box plot are going to be the range and also the IQR. We can quote those numerically for somebody by taking them down here at the bottom. We can find the, trying to get it nice and pretty on the screen right here. Gonna make this. There we go. The range for the box plot is going to be the distance from the min to the max. The distance from the min to the max of the non-legendary is 145, min to max. The distance for the legendaries is 55, 85 to 140. The IQR is 45, 40 to 85. The IQR for the legendaries is 20. Notice how the legendary Pokemon have less spread to their data. We can see it both visually. So legendary Pokemon are actually or not on average. The legendary Pokemon are typically faster via the 50th percentile, 60 to 95 compared, and they have less variation, a smaller range in their values, and additionally a smaller IQR, range of the middle 50% of the speeds of the Pokemon for that group. These are the things we'd want to hear in your write-up. Additional quick thing right here before we do the Canvas content, if you want to go the extra mile, which is not required, you could go here to analyze and tabulate. Where's my tabulate? Tabulate is found under, I rarely use this, but it is a cool tool. Did they move it on? There it is. Analyze, tabulate, I said it. Analyze, tabulate, and you can go here and put the legendary, put it right there. And we've got legendary, and we want to put here speed. I so rarely do this. Can I do this? There's the sum of the speed. We don't want that. We want the min and the max. There's that. We can drop this right here and compare the range, but that didn't do it. Can I put it right there? There we go, the range. We could compare the medians. And we can compare the interquartile ranges. And there we go. I wonder if you can just do a difference over there. Can you not do the difference between them? Good things right there. Yeah, you could do a certain, you do a quantile or something. There's quantiles. Give you all the quantiles. Oh, you can choose a quantile, like the 75th quantile. So lots can be done right here, and then you hit done, you get this nice little table. So you could make your own table of numbers. Not required, but these are some of the neat things Jump can do to summarize data with Tabulate. But then you can easier look at the legendary versus the non-legendary. And you've got the median for legendary is higher right here. And you can see that the range is smaller, the IQR is smaller, and I don't know, you can compare 70%. Whatever you want to talk about and compare, the point is to compare and contrast the distributions on ideas like shape, center, spread. So let's look at the questions, make sure we've done well at these and we have answers to them, because the rubric is how you're graded, so always look to see if the rubric has been answered. So write-up includes, that's Mosaic plots. Okay. Here we go, proper screenshot. Make sure you have the 5-number summary included in the graphic. So if you want to see, make sure your screenshot looks like the following. Oh, we didn't screenshot it? Go over here. This would have the 5-number summary included. If a grader takes off points, let me know. And we're going to click here. We're going to go right here and go like this. Don't get extra. If you do get extra, remember in Microsoft Word, go in, paste your screenshot. If you have extra stuff you don't want, click the picture format. Do not get the top of your screen. Do not get the bottom of your screen. Have a good screenshot that'd be professional in a report. I do like this little black border right there. Make sure it doesn't cut off parts of the image. But now we have a good looking professional picture right there. And next we have, this is just a write-up, proper screenshot, and right, well, there we go. Write-up includes numeric information about the nature of the relationship between the two variables. Write-up describes the nature of the relationship, use differences and similarities, like the numeric values given on center and spread. So that's got it. That is Data Analytics 3. We're gonna do Canvas content now. Let's do it. Who all's here right now? I need some what's up in the chat. Let's throw 100 points if you're here. We're gonna do some Canvas content number 3. What up, Skylar? We'll do Reese, let's go. 100 points for you there, Reese. Blakely, good to see you. What questions do you have? Were people doing data analytics and following along? Thank you, everyone. I guess you were here following along. I love it. We're gonna do Canvas content number 3. Let's not do for a little bit, right? Started. Okay. This is a really good Canvas content. A lot of people say, what does chapter 5 look like? Alexander, good to see you. People say, what is chapter 5? Let me go to the segment. Okay, we're gonna mark the time right here. And we got 28:43. Stat 201, Canvas content 3. People ask me all the time, I'm ready to beat chapter 5. Oh my gosh. Let's do it. Let's beat chapter 5 right here. Let's take it on. So people say to me, what does chapter 5 look like on the test? What does chapter 5 look like on the test? Does anyone know? What do you think chapter 5 looks like on the test? What do you think it looks like on the test? Just take a wild guess. I want you to know this. I want you to say this. For 50 points, chapter 5 looks like the what? Like you say, well, how would I use the applet on the test? What's chapter 5 look like? Looks like the Canvas content. Reese knows right there, 50 points. Both versions of this, you bet. We'll do 2 versions of it. Might cover your questions. Let us know. We can do more versions later. We'll do 2 versions now. Then we're going to do chapter 5, part 2. Canvas content looks like the test. So if you wonder how the test is going to look and how we'll have you use the applet, looks like the Canvas content. Okay, let's start at the first question. Someone just skipped through that and they're like, what's the test look like? It's Canvas content. The Chocolate Boom candy company manufactures many different types of candies. The most popular Valentine's Day candy box follows a distribution with a mean. Okay, so once we are here, we have heard notation.
Notation,
I met Leo. Shout outs to Leo. He's like, I'm Leo. And I was like, who? And he was like, notation. I was like, oh my gosh, why didn't I realize that? Saw him at Haslam. Shout outs to Leo. So with this right here, he's a real person. He exists. When you hear the mean, you should think what immediately? When you hear the mean and standard deviation, and your candy box weighs this, find the z-score. What notation? We practiced a lot of notation yesterday. You should know the notation.
Notation, brother.
What notation do you think of when you hear mean? Mean. Standard deviation. Mean. Mean. Standard deviation. Mean. Mean. SD works for standard deviation. Yes. I'll give you 50 points for that. Go further. Mean. I'm accentuating one letter in each one of these. Mean. Standard deviation. What is the notation for these? Oh, if you get formulas later, you're like, I know what that means. Give it another 5-10 seconds. Take a guess. Don't worry if you're wrong. Don't worry about being wrong. Just take guesses. You only know if you're wrong if you say it, and then you're like, we got mean, standard deviation. So if you're trying to memorize these, it's mu, 100 points right there, Reese. It's mu, mean, mu. So this is the mean, and it's mu. So like it's like a U, but it's a mu. You can make it look like an MU, mu. And then sigma, great job, Alexander. Sigma is standard deviation, and Y is what you see or observe. You can also call it X. Oh no, yeah, you're like, what are you asking, Brian? Thank you for a clarification. And so we are trying to find the z-score here, which is literally how many standard deviations something is above or below the mean. So z-score equals observation minus mean, which is a difference, divided by standard deviation. And we plug in our numbers right here. We observe our candy box being 467. We subtract the mean. We're going to get a negative z-score. And we divide by 15.2. And whatever this equals to is the answer to the question we are trying to solve for the z-score. So, oh, no worries. You're caught up now. I like that. Okay. 467 minus 486 divided by 15.2. There you go. We are 1.25 standard deviations below the mean. So this is a lighter candy box than we would have expected. Now, this is where usually people get stuck. But pro tip, you have to practice this and do this. I'm going to do it for you now as though I don't know how to do these questions. What you would do first, you would take this information right here. What does that info mean? You have to know what this means. So help me on the chat. What does this info mean? Can anyone help me with this? That info right there that I've highlighted, it's actually shape, center, spread. But shape, center, spread, what are we talking about? This is the shape, the center, and the spread of it. What am I talking about? What does that mean? Capital N 98.207? What does that mean? What are we talking about? Any ideas? Throw me some ideas. You don't know what this means? Write it down. Who knows? I'll start giving some tips right here. Normally distributed, capital N is normally distributed, and then 98.2 is the mean, and then last but not least, I should have done color coding there, the standard deviation is 0.07. You go up in units of 0.07. The mean and standard deviation normally distributed with a mean and a standard deviation. So the capital N means normal, and then the next two numbers are mean and standard deviation. So 98.2, 98, oh my gosh. Let me disappear. 98.9 and 98. Well, how am I getting these numbers? How, as I can't do them in my head, how am I getting these numbers? Does anyone know? If I make a mistake, let me know. Anyone know how I'm getting these numbers? How did I get those numbers? How did I know these numbers down here? How did I get those numbers? Thoughts on that? If I made a mistake, let me know, but I don't think I did. What's the key to getting these numbers? People say, how are you doing that? How do you know those numbers? Every one of those numbers is one standard deviation up. Exactly, great job, Reese, right there. You just go up standard deviations, you go up 3, you go down 3. Now, when you do this, I ask that you do the following. You write the z-scores below. You put 0, 1, 2, 3, -1, -2, -3. So these are the z-scores right here. How many z-scores they are away? Exactly. Great job, Reese and Skylar. So now we have the z-scores listed out below the curve, and we have a curve that is normally distributed with a mean of 98.2 and a standard deviation of 0.7. So that information needs to be displayed here properly. Write the z-scores below this. So here's my pro tip. When the test starts, you cannot bring this to the test. Write this down. We could go a little bit further. We could add extra things, but at least have this. Draw a normal curve and practice doing the problems like I'm doing this now, where you have the normal curve drawn out, and then maybe you add in information such as like 68. The empirical rule, which you get those numbers on the test, so you could flip to a problem on the test that gives you the numbers and write them down on your curve and draw as best you can the numbers and put the values on the curve. So 68, 95, 99.7. And now you've got a pretty good drawing, and you could add extra things like 16% here, 2.5% here. We could go over all the steps to get all these numbers, but the more you practice with these numbers, like Reese and Skylar, have you kind of memorized some of these numbers right here? Have you, at this point, some of these numbers, you're just like, oh yeah, 16%, and you can double check your work too by seeing if it adds to 100. So we're going to do this problem here, but this graphic's going to help us immensely in a moment. So you can do 50% above here, because 50% would be at or above. And this will help us answer so many questions. Oh, no worries. Yeah, what are you confused on? Let me know. Skylar, what are you confused on with the numbers? So let me explain how we get to 68. If you're confused on that, let me know what you're confused on. 68 is the area between -1 and 1. That's just what we'll give you that on the test. We'll say that. So we're saying between z-scores of -1 and 1 is 68% of the data. Like if you had a race and the average time was 20 minutes, there you go. And those numbers, yes. So I think you get that. That's what this central 68% is contained between. But the 2.5, let's talk about how to get that. If 95% is inside of here, what is total outside of here? So I want you to think of just visually and mathematically, how much area are these pink areas worth? Like total. If the yellow area is 95, then how much are those pink areas worth? If the yellow areas are 95, how much are the pink areas worth? Total. I want you to have like an moment where you realize it. What would be the total of the pink areas? If 95 is inside, and this curve is 100%, that's the key right there. The curve is 100% of the area, 95 is inside, then what's the remaining 5%? So now think about this, there's two of them. So you would take that 5% and cut it in what? So you would take that 5% remaining outside and cut it in what? Exactly. So then it's 2.5. How much total is outside of 97.5? How much total is outside of 97.5? So 97.5 has how much total outside of it? 97.7, 99.7. Oh my gosh, I can't speak. 99.7. 99.7 has how much total outside of it? 99.7 has how much total outside of it? 0.3. And then you take the 0.3 and cut it in half and get 0.15. Is that, great job, scholars, is making more sense? And that's where we get the 0.15s from. And then if you want, you can always put the area between the numbers, like this area right here, from here to here, would be the difference between these two arrows. So this area is 2.35. This one is the area difference between the next two, 13.5% of the data, 34, because that's 16 minus 50. And this one is the 0.15, which goes all the way over to the side. Is this making more sense, Skylar? If you take a moment when your test starts and write all of this down, like you just try to mark as much as you can on your curve, that way you have information. It's going to be a huge help. Yep, and it's just try writing it down. Try saying like, well, how do I get this? What does this mean? And 13.5, did I delete? I deleted one of them. This goes here or something. 1, 2, there it is, 2 standard deviation. And then this is 2.35. My curve is getting cluttered, but you can see it right there. And try writing this down, try drawing it out. The better you can draw it, the more you can draw it, the better you get at solving these, and the problems get way easier. So now this gets us to our question. Our question right here that we have. Notice we spent a lot of time working on this because now we have this question. It says the area outside of these numbers is 0.13. It wants to know what percent of adults are higher than 99.26. So what it's telling me in this graphic is that the total area here is 13%. You can put it, I would draw the curve. That's a huge thing right there. I would draw the curve. That's the best thing to do. Good question, Alexander, right there. So think about this. If that's total 13%, then inside of here is 87%. But the answer we want, what we have to find right here, is just this area over here. We have to find this area right here. So how are you going to find this area mathematically if both of those areas are 13%? So both of those areas together are 13%. Think about what we were just doing. This is very similar to what we just did a moment ago, but with different values. Because we know that between these numbers is, like saying up here, between these numbers is 13%. So how do we find just one of them? So what would we do to this number right here? Because this is 13% if you take both of them. And hint, they're symmetric. You can check by finding those z-scores. The total area there is 13%, so how are we going to find just one of them? The hint is they're symmetric. Does anyone know? It's 13% total. Divide by what? You got it, Skylar? Yeah, by 2. That's it. 100 points. That's it. It's just like we were doing a moment ago. Kind of the inside out. It's like, well, okay, it's symmetric on both sides, so we just want half of the area. Divide by 2. W, Skylar. So that's Skylar, another 100 points. Great job, Skylar. It's knowing how to draw these and practicing with this. Yeah, exactly. So you just take 13% or 0.13 and divide by 2. How does the normal probability plot determine if a distribution is normal? Yeah, I love those W's in the chat for everybody. A normal probability plot is a plot that shows us the probability a distribution is normal. It's used for univariate quantitative data, and it's not a linear relationship. We don't talk about, I'm making tons of stacked histograms right here. These are just multiple stacked histograms right now. And what we're going to do right now is we're going to go to normal, and they call it a normal quantile plot. I call it a normal probability plot. The ones that are the most normal here are going to be the ones that do the what the most. This one's the most normal, and look at the histogram. It has an outlier over here, but that's the most normal so far. That might be the most normal. Oh, that one's, it's kind of integer data. But the most normal, is it this one? This is the most normal. So why is this one right here the most normal? Of all the quantitative distributions, this looks the most normal to me because it what's the what the most. So the reason it's called a normal quantile plot is you're matching up the quantiles of your data with the quantiles of the normal, and it makes a line showing you that relationship. It follows the line. So the more it follows the line, the more normal the data is. And if you go to one that really doesn't follow the line, I think it was higher. Oh, okay, that one's, it's got a little skew to it. Notice the pull at the end. Still kind of normal-ish. But where's one that really deviates? That one has more outliers. Notice how it doesn't go linear at the end. This one has weirdness. Yeah, I can show you some really not normal data if you want. But the ones that deviate, if it's really not normal, what you'll see in a normal quantile plot is you'll see the line, and then you'll see the data do something like this. Hint for the MyPearson, this is a right skew. So if you were to plot the histogram, it would look something like this probably right here. It'd be right skew. I draw Mr. Squidward over here on the side, just like being like, woo, just, there you go. We talk about that in class, Squidward, that's how our class goes. Just a way to memorize it. We don't have skew on the test, but if it follows the line, it follows the normal, because the line is the expected normal. It's not a linear relationship. A lot of people start saying that on the test because we teach you linear regression. But if it should be if the data follows the line. If the line is straight, like if the data points follow a straight line. So if the data points follow a straight line, it would be p-values are used for the Shapiro-Wilk test for normality, a goodness of fit test it's called. So we can actually do that in JUMP. That's not the answer to this, but you can do a test for normality, and that would be done under here under continuous fit, normal. And then we need to add in the test, a lot of steps. And this is the test for normality over here. And if the p-value is low, we reject normality. And we're actually rejecting normality for all of them. They do two. They do the Anderson-Darling and Shapiro-Wilk. Just different bunch of statisticians. Shapiro and Wilk and Anderson-Darling came up with tests. It looks like actually via statistical tests, none of these are normal due to low p-values. The goodness of fit test tests a normal curve on your data and sees if the normal curve is a good fit. And if it's a good fit, the p-value is high. Now that's only the result of a goodness of fit test. P-values do not stay the same or do not interpret the same for everything, other than when the p-value is low, reject the null. When the p-value is high, just let it fly. More on that in later chapters. Next, ooh, I love it. This is some of my favorite stuff right here because we've got the really good stuff. So here is a question you would want your graphic for. So we have our graphic over here. We drop in the question and we take a look. Now, if I've drawn this out, what am I going to do on my graphic below? If I've drawn this out, I've taken all the time at the start of my test, I've done Brian's pro tip, and I've taken all the time to draw this out. What am I going to do? I'm going to erase my numbers of the context. What am I going to do? If you've taken the time to draw this out, you're going to see how easy this question is now. What are we going to do? What are we going to do? Put in the new numbers. Great job right there, Reese. So the numbers were 25 was the center. The standard deviation was 8. And you only have to go up to, or 3. My gosh. The standard deviation was 3. And so what percent of data would be above 31? What percent of data would be above 31? Look at, we spent all this time drawing this graphic, and now it says what percent of data would be above 31. We didn't even have to draw in all the numbers. 2.5. Answer solved. And you can even see if you take some time to work through the question. 31 is 2 standard deviations above the mean. 95% is within plus or minus negative and positive 2. Outside is 5%. Cut it in half, 2.5. And then you've got the visual down here to confirm the answer. You can even go a step further if you want and shade the rest of it in. It's not 2.35. Easy money, just free question right there if you draw it out. Please draw, pro tip once again, draw the curve. And it's not 2.35, it's 2.5 because 95 inside, 5% outside, 2.5 in either hand. 95 inside, 5% outside, subtract from 100, and then cut it in half to get the 2.5 in either hand. The finishing times of a local race was this. Below 22 minutes. So guess what? It's the same stuff right here. Now it's below 22 minutes. Can anyone for 100 points answer this before I get the drawing even done? Oh, you got to go quick. I'm going to draw slowly. Whee! I'm going slowly. I'm panning up so you can see it. I'm disappearing. Oh, answer incoming. My drawing's not perfect. That arrow should be right there. There's the answer. It's 16%. 100-point scholar right there. So it's 1 standard deviation below the mean. Mean of 25, standard deviation of 3. The observation is 22. 25 to 22 is a 3 units, which is 1 standard deviation. We have the z-score marked below. And with that, 68% is within plus or minus positive and negative 1. And outside would be 32. Cut it in half for the 16, and you got the answer right there. So remember, drawing this out is a huge help. Huge. We just burned through those last questions because we had a big drawing that we spent a good bit of time working on. Draw it out. Whole house knows what they're talking about. 100. What'd I do wrong? Wait, what? Incorrect. 99.26. Does it say answer as a percent? If you got this wrong, let me know. Let me go fix this. Let me go fix this on my class at least. 2 seconds. Fixing the question. That question seriously say or doesn't take it as that. We usually do the alternate solves. Brian got a question wrong. Here it is. Go question details. Here it is. Question bank. Oh, and you're literally seeing the answer now. 0.065. No margin of error. Oh wait, margin of no margin of error. Good, go. Got it. Okay. Taking away the margin of error though. Okay, the question's been updated. Making sure okay. I think we're good. Let me leave the question test bank. Many of them right there. But now, and I'll maybe tell Terry, because I want to get that updated, say, so you push it out. But that right there, it should have the alternate solve. We just try to standardize the way you answer. So that way everyone answers similar-ish, and then we can grade it easier. It makes grading easier, but then it's still right if it's 0.065. So good stuff right there. Okay, Doke, let's do one more preview of this, then we'll do some Chapter 5 quiz. Good stuff right here. Did Jerry do good on this test? Yes or no? He made a 77. Did Jerry do good on this test? What are your thoughts? Did Jerry do good on the test? Yes or no, and why? He made a 77. So once again, this boils down to knowing notation. We can't state that enough, that you have to know your notation. This is very similar to the first two questions we did right here with this. So did Jerry do good on the test? Please, if you have a moment right now, write down the notation that I'm about to do. Did Jerry do good on the test? Do you know? What does chat say? You'll notice that the mean, mu, means population mean. That means if you had all the information on everyone who took the test, you could see the average for all students. The standard deviation is the variation. Now you might say, well, what does variation mean? Well, it's a standard deviation. So when you think about what a standard, he did do good, right? Skylar, you're right. Why did Jerry do good? Yeah, you did pretty good, Jerry. Why? We'll see in a moment, or you can say. With this, if you say what a deviation is, that's like, how far are you away from things? And you're asking, how far do things typically differ from the mean? And if you look at the formula right here, the sample standard deviation formula is the sum of the squared distances of the observation from the mean, and then you square root it after dividing by n-1. Oh, nice job. About 1.166, I think. And so you're looking at how far are things away from the mean. And think about this, if I were to just divide by n, and let's say we just, like, think about this. I wish the formula was this, but it would turn out to be 0. If you were to look at this right here, this would literally be, or we could do the sum of it. The sum of the differences observations are from the mean on average. Does that make sense? We have how far away are observations from the mean on average, because you're doing it. This is what a standard deviation is. It's like an on average deviation. How far are things typically? And when you think about the way the curve looks, one standard deviation incorporates most of the data, 68%. So most things are within one standard deviation, like the typical distance from the mean. Now you might say, well, why do we make the formula more complicated? If we did this up here, it would be 0 because things are above the mean and below the mean. So it kind of averages out to 0. If you did this formula this way, you wouldn't square the differences and get a positive quantity of differences. So what we have to do is we have to square the differences to make a positive quantity of differences. Then even negative differences are positive. And then we square root it to bring it back to non-squared units, because if you have it squared, it's called variance. If you square root it, we call it standard deviation because it's in units of the problem. Variance is squared units of deviations. And then we do n-1, which is kind of a correction for small sample sizes where we wouldn't get a lot of the outliers, and thus minusing 1 makes it a bigger quantity because we've probably underestimated it for smaller sample sizes. As n approaches infinity, the differences between n and n-1 go to 0, at least conceptually in terms of distance, and thus we get really the same calculation for larger sample sizes had we used n or n-1. And that's the whole theory behind the calculation of standard deviation and why we use it. Now, what does it mean? Well, think about what would have a standard deviation of 1. What would have a standard deviation of 1? The cost of a fast food sandwich, or let's say running yards for an NFL player in a year. What would have a typical variation of 1? Running yards or fast food sandwich? It can be in yard units or dollar units. What would have a standard deviation of 1? What would have a standard deviation of 1? Not running yards. Good answer, Alexander. It wouldn't be running yards, though. it would be fast food sandwich, because we could say a fast food sandwich, like, and we're not talking a super fancy one, usually costs about, let's say, $3 these days with a standard deviation of $1. And unless you're getting it free, which is pretty rare, that'd be an extreme outlier. But the mean is $3 for like a decent fast food sandwich. And then the standard deviation is $1. So it's probably the fast food sandwich has a standard deviation of $1 with a mean of 3, where running yards might have a standard deviation of 200. Alexander, we're throwing another 100. Just keep those answers coming. And then what you do right here is you would say most of the NFL players get between 600 to 1,000 yards. And notice it's causing, or it's showing us the variation here. And we can use the same normal curve, and we can talk about the central 68% of data. Does that make more sense why we talk about a standard deviation and what a standard, like what is the typical variation, standard or on average variation? You could just say average variation or kind of expected distance things are away. Like things are usually about 200 from the mean. That's what standard deviation means. Like a fast food sandwich is usually within about $1 of each other. That's what a standard deviation is in a kind of simpler way of understanding it. People are usually about 200 away from the average of what we see for running yards. Yeah. It's like I want people to know what these quantities mean, because it's like everyone knows what the mean means because it's just the average of the observations. But then people are like, what is standard deviation? It's just like, how far are things averagely away? Like, what would you expect if a fast food sandwich costs $3 on average? Well, what's the typical sandwich going to be around it? Well, about $1. And we could find it out mathematically from the data, but really good understanding right there. I hope that helps. And then someone's like, whoa, I didn't know what that meant. What?
Wow.
Even Owen Wilson's impression. Okay, so for this one right here, we do observation minus mean over standard deviation. The observation is 77. The mean is 70. Standard deviation is 6, telling us the z-score of 1.166. So what do you think is the biggest downfall of chapter 5? Yeah, using the applet and using the empirical rule. People just can't do applet questions. We'll do a ton of them. I'm gonna double check my work right here. That's what I thought. People just can't do applet questions. Reese, 100 points, keep asking those questions. That's the big downfall. We've done these empirical ones a lot. So check out a moment ago, we draw out our graphic. Below 22 minutes, we need to go to our graphic that we have, that we spent a lot of time working on here. And below 22 minutes, since it should be posted soon, very soon. Check out the review videos right now if you want. But below 22 is right there, and we walked through that a little bit quicker, so that's 16. Above 31, we did this one earlier, we're getting the same questions, and this is the same one we got earlier. Let me do one more version, see if I can get something different. Check out if you're wondering, and we did the Candy a Boom one also. So we got a lot of the same questions. Okay, the candy weighs this, subtract the mean, divide by standard deviation. There it is right there. Hopefully I got 100 this time. No mistakes. 10 out of 10? Are you serious? What am I doing? Oh no, I got a 10 out of 10. I saw the 8 out of 10 from last time where I didn't do the decimals properly. Or did I? Oh, be careful. Do be careful. You're copying my answers. Your class might not have this answer. I updated ours, but be careful. Be careful, careful. Oh, it said 8 minutes. I thought it said 8 out of 8 or 8 out of 10. I was mad. Let's do one more version of this. Oh, you made changes. Save it. Save my changes. Okay. One more version, then we're going to do the steer weight questions coming up here. We'll look for the different ones because we've already done this one. Below that, the problem is a lot of people probably see my answers and then they see, oh, that's the answer. Here we go. So, Reese, you were saying, which questions do people get stuck on? It's this one. But here's what I want you to do. When you start the test, immediately draw your what? Immediately draw your what? When you start the test, immediately draw the applet. Exactly. So you should have a picture something like this. And you could draw the areas on the curve. You could replicate this down below. And below it, you're going to put 98.2, 98.9, one standard deviation up, 90. And actually, that's all we really need to put because this will get the answer. I already know this because I've done the question. You could put all the numbers, but these are the only questions. Great job, Reese, right there. You know what's interesting? If you put your 68 on this, here's a very good question. What percentile are we at one? A z-score of 1 is at what percentile? 100 points no matter what you say. You might say one thing. I know what you're probably thinking. You think 68 is not 68. You might think another number. It's not that number. You need to go a little further. We have to know what percentile means, and it means area below, area below. So what do you think is the percentile of a z-score of 1? What percentile is that at? Oh, good. That is very... That might... Wait, is that it? It is 84. Reese, good. Reese, you were very close, Reese. Good work. Points in the chat. It is 84. The easiest way to get this is to say 16 is above, and if 16 is above, 84 total is below. Does that make sense? Because you could go through the arrows, like you could cross over the arrows and say like, okay, we just travel down the pathway. You can also add up all the areas between, that works too. Just double check your numbers, and the easiest way a lot of times is to say, well, 16 is above, 84 is below. And with that in mind, this is the 84th percentile, and we are looking for the 80th percentile. Where's this? What percentile is the center of the curve? What percentile is the center of the curve? Like the very, very center, the peak of the curve is the what percentile? The 50th. Great job, Skylar, right there, the 50th. So I would bet the answer we're looking for the 80th is somewhere between these, and it's probably, wait a minute. This is marked for us. Almost like they want us to see this. Almost like they want us to see this. Like that line right there that goes down to right here. And you know what's interesting? It wants the what of the 80th percentile. It wants the what of the, like read the start of the question. What is this for the 80th percentile? Like read the question up there. It wants the what of the 80th percentile. The body temperature. Like, do you have a guess of the body temperature for the 80th percentile? Do you just have a guess of it? I mean, you can see the numbers I've written down below. Do you have any sort of guess for it? Like, I don't know, maybe this? You gotta read my bad handwriting. 98.7. You know what? 98.7. Watch this. I think there's a good shot. You were right. Reese, 100 points. You did enough work, technically. You figured it out. We're going to show how the rest of the solve can be done. But just looking at it visually, you're like, it's on 98.7. Reese, look up. I don't know the face. You can't, you're killing me, Smalls. Quote a old movie. Yeah, it is an old movie now. Okay. Me right now? Yeah, he did it. That's the answer to the question. But let's see what information we're given here. We're not told the answer. We are told for this problem the what of this. So we're not told the answer, which would be down here. If I wrote the answer, it'd be down here. So Reese solved this down here. But we are given the information here, which is not the answer. So look at where I'm highlighting on the number line. And we're given that information instead. Well, I did the negative. Ignore that. Not the negative. We're given the what instead. We're given the what instead of the answer. We're not given the answer. We're not given the observation. We're given the what instead. Well, this is the good point. So we'll erase what we have right here because this was helping us estimate. We're just going to erase that extra erroneous information that we added. Not required for the solve. That's extra nonsense. We're given the middle 60%. And if this is the middle 60%, then that's the top 20 because it's symmetric. And this is the bottom 20, making this literally right there. That is the 80th percentile. So field included on that. That is the 80th percentile. And this is the what of the 80th percentile. That blue mark and that number is the what of the 80th percentile. That blue mark is the what of the 80th percentile, that number. Not the temperature. The temperature is, we wrote in some context here, the z-score. That is the z-score of the 80th percentile. That is the z-score of it. So the z-scores are on the 0, 1 curve, but then I wrote the context below, and that's how we were able to solve it so quickly, is we just put the context of the problem with the numbers from the actual curve, because it told us a mean of 98.2 and a standard deviation of 0.7. We put those numbers below, and we just looked, and we're like, well, looks to be close to there. So now we're going to do this right here. The positive z-score is right there, and that is where the 80th percentile is at, because 20% is above and 80% is below, because the middle 60%, 40% outside. Please slow me down if I'm going too fast, especially if you're here. What we're going to do is the z-score tells us 100 points for Reese. What we're going to do is the z-score, we would take the mean and we would go plus z-score times standard deviation, because we go that many standard deviations above the mean. This is it right here, Alexander, because think what a z-score tells you. It's how many standard deviations you are above or below the mean. So we plug in the z-score of 0.842. We times it by the standard deviation of 0.7. We add it to the mean of 98.2, and that's it. We do this sometimes without realizing it. Like, it's funny to me how much we know about statistics that we just, like, I've taught you that you're like, wait a minute, I know to do that. And this is just the math now. You were right there, Reese. If we annotate it or delete decimals. That makes sense. Nice job, Alexander. Because watch this. If your test, if I tell you, great job, the z-score on your test was 2.5. Here's your z-score. And I say your test had a mean, it was normally distributed with a mean of 70 and a standard deviation of 10, then what was your observation? Oh my gosh, this pen is messing up. Don't do that to my pen. Don't you do that. What was your observation? So if I say your test had a z-score of 2.5 and the mean was 70 with a standard deviation of 10, what was your observed test score? Boom, Reese, you got it. And isn't it interesting you do that one? Like, it's the same problem, it's the same information, but you're just like, oh, I'm 2.5 standard deviations above the mean, and this one's just more decimals. The answer is 0.842 standard deviations above the mean, because that's what a z-score is. It's how many standard deviations above or below the mean an observation is. So you just go to the mean and you add or subtract, depending on positive or negative z-score, that many standard deviations. And we show the form, or we showed the formula just a second ago. But I think once we do more decimals, it's like, wait, what am I doing? So there is the solve down there, the mean plus or minus, or plus the z-score times the standard deviation. Really good work, really good questions, and let's do the MyPearson. Great work. Chapter 5 is a tough one, but it's one of my favorites. The normal curve is super duper important, no matter what Jordan Peterson says. Talking bad about the normal curve, don't you do that to me. Stat 201, chapter 5. Part 2, MyPearson. Okay. So with this, I think the steer weight one, it's one of my favorite problems. I actually find them fun. Weird. Well, weird guy who likes stats. So. Chapter 5, part 2. Wrong button. You'll be crazy. Oh, wait. So IQR, middle 50%. If it asks you for the IQR, click the middle button. And we're going to bring up the applet and pin it in the chat right here. Thank you to Adam Spanbauer, absolute pro when it comes to coding. Here's the applet pinned to the top. And let's do some chapter 5 quiz part 2. We're gonna do those steer weight questions. We can do all of them. I think we got enough time to do the full quiz. Okay. Get the applet up here. Okay, start with the main screen. So with these questions, we're gonna go to the steer weight one first, because I think Skylar requested it. Here we go, steer weights, good. Okay. So whenever you're using the applet, you might be presented pictures on the test. So what we can do on the test, instead of having you use the applet, is show you pictures. We just did some a moment ago with the Canvas content, which is what the test looks like. So go check that out and watch how we solve this. To round to 1 decimal on them. So when you're doing this right here, this wants you to round to 1 decimal, and it says the cutoff weight. So we're going to put round to 1 decimal up here. So round this to 1 decimal, and then important to know, we are trying to find a position on the curve, an X position, using the probability, which will be right here. So we're using the probability to find an X position. So you must now go in and enter in the mean. There's the mean and the standard deviation. Given by the format, the curve is normally distributed, hence the shape. Mean, oh, no worries, Blakely. No, Blakely, we got this. Perfect time, Amy. Good to hear that. So with this right here, we'll throw everyone 100 points for being here. We have the mean and standard deviation, and now we want the top 10%. Why is this the top 10%? Explain to me conceptually, why am I showing you the answer right now, which is the top 10%? Over there on the left, why is that the top 10%? I didn't put in 10%, but it is the top 10%. It's the top, because it is, right? It's the 90th percentile. The 90th percentile is where the top 10% is. You can do it a lot of different ways, like between, and that is the answer right there. This right here would be the answer for the top 10%. Notice how it doesn't change. Or you could do 20% on the outside, and there's the answer right there. So the best way to do it probably is to do the top 10% and to do this right here, and there's the answer. Do remember that percentile means area below though. So you could do the 90th percentile, which is where the top 10% is. Where's the lowest 20%? There's the answer. Notice we can display the answers in a lot of ways. I know I've typed in 80%, but you have to look at the curve and understand what it's showing you. That's why I'm doing it slightly different ways than just typing in 20%, because the top 80% is the bottom 20%. Like the outside 40% is also where the bottom 20% is. Does this make sense in the chat? There's a lot of ways to visualize this, and that's why I want you to see that you could just go the classic visualization here, but you should understand if 40% is on the outside, that leaves 20% in either tail. If 60% is on the inside, 40% outside, 20% in either tail. So this is the deeper understanding. Great job, Alexander, right here. Like the more, like this is just the classic solve. If you want to do that right there, it works, you get the answer. But then understand what you're seeing with the graphics. So when we show you graphics on the test, you can do it. Next, we have the middle 40%. Once again, we can do different ways of doing this. Like the outer 60% would be the answer. This is because 60% on the outside leaves 40% on the inside. But we'll go classic right here so we can see the middle 40%. And take the numbers down here. 1110.3 and 12.0. Wish it rounded in there. Should be good. There you go. That's how to do that one. Love these questions. Here we go with an IQ one. Dun, dun, dun. Now this is what I really like. You do these questions as many semesters as I've done them. Or I ask this of you. I ask you to guess at these. How many of these do you think I'll get? 1, 2, or 3 by guessing? How many of these do you think I'll get by guessing at them? 1, 2, or 3? These are kind of tough today. Sometimes they're easier. Sometimes I get easier versions. These are kind of tough. Okay, so let me guess. Above 80. That's a z-score of 1.25. Below 1.2816 is 10%. So it's going to be like 89.6. I go, Amy, you got too much faith in me. Well, I'll show you how to solve these in a moment, but this is tough. Below 95 is below the center. That's a z-score of, it's like a quarter of a quarter. So quarter of a quarter is 0.3125. A quarter of a quarter is 0.3125. So that's more than 25%, between 25 and 50. Falls off quickly. That's gonna be like 31.4. If I get that one, that'd be amazing. The next one is between 0.5 and 2. That's going to be less than 47.5. And it's going to cut off the majority of the 34. So we'll cut off 22 out of that. 47.5 minus 22 is 25.5. How many of these did I get? 0. Let's see how close I got. Okay. So these were my guesses, and I hope they were close. If you want to try these on your own, try drawing the curve and visualizing how they look. Let me just show you what I did. What I did right here is I did a quick sketch in my head where I took the curve and I said the mean of 100, and I went down to 84, and then we'd have 68, 116, and 132. I think that encompasses most of the numbers. 80 was here, and it wanted above 80. So you can use your own estimates, because if you notice, that has the 50% and the 34, so it has to be more than 84. What I'm saying right here is this is 34, and this is 50. So the area is more than 84 using the numbers from the empirical rule. That's how you could estimate it. The next one asked us if we were trying to find the area. I got to double check. The area below 95. 95 is a super hard one. Yep, we did it. Yep, Jonah, at the start. Check it out. 95 is right here about, or 95. Oh, did I get that? Yeah, 0.31525. What would you do with 300 viewers? We had 300 viewers live. I don't know. I'll throw out 1,000 points or something. Yeah, that'd be crazy, Alexander. I have no idea how that would happen. We don't get those moist critical numbers here. If you notice, this is less than 50. And he gets like 3,000, 30,000 almost sometimes. This is less than 50, and so it's between 16 and 50. Does everyone see how if you use the empirical rule numbers, that green area below would be between 50 and 16? So that's how I was guesstimating that in the shorthand, between 15 and 16. And then also we have the last one. The last area over here was between like 104 or so and 132, which we know the area between these is half of 95. So half of 95, if you take the 95 and cut it in half, is 47.5. And then it's not quite that, because we'd have to shave off that extra area. If you're wondering how I was guesstimating these, that's how I was doing it. And now the question gets easy. Now the question is very easy. Because what we're going to do is we're going to enter in the mean and standard deviation. And then we're going to find the area, find the probability using X. First one says above, so we go above and we go to above 80. And the exact answer to one decimal, which we need 3 for, is 89. You got to be, Amy, are you seeing this? 89.4. Does it even, I was off by 0.0016. If I had just gone to 89.5, I would have gotten it right. I was off by 1/10 on that one. Don't tell me I'm off by 1/10 on all these. Oh, 1. I know, right? I'm guessing these, and it should give me a little more leeway. Now we go to below. Make sure you've clicked find p-value using X, because we're finding the probability using the X value on the curve. And we're going below 95. This one was tougher. This is a very tough one, just because towards the center of the curve is a lot of area, so it's hard to guess those. This one I have a little more confidence in. We'll go to between. And we go to between right here, and we type 108 and 132. And it was closer, but the first one was the one I knew a z-score for more directly. So those are the answers. And notice our numbers were not that far off. We were able to take good educated guesses. I know, right? All is one digit. So the first one I really thought I was going to get at. But I don't know if I've ever gotten a 3 out of 3 on this one, but I've gotten 2 out of 3. I'm pretty sure. I know I've gotten them before, but the more center of the curve they are, the more the curve changes rapidly. It's hard to know exactly how much area. Towards the ends of the curves is more obvious because it's very small numbers, unless it wants like 4 decimal accuracy. Here we go with the football one. Football. Taylor Swift just won the Super Bowl. I'm kidding. I mean, yes, but no. Let's go with the football question here. Stat 201. MyPearson. Chapter 5, Part 2. NFL. NFL data from the 2019 season, which is forever ago now, has 508 receivers. The mean is this. The standard deviation is this. Now, here's the thing. If we plot this data, what do you notice? If we plot this data, think about if you're in the NFL. Look at the numbers on the bottom of the curve. That's not right. I need to reload the page. That's not right. Numbers don't even really matter because, oh, did I put them in the wrong spot? It was like 200 and 300. Steer weights, did earlier, percentiles? Yeah. So notice this data would go negative very quickly. That is a bit of an issue. Something tells me that this data not normally distributed. Because if it was normally distributed, the data would go negative very quickly. I just put in some guesstimates of the numbers over there. So the data is extremely right skewed. You know him, you love him. He's back, Mr. Monster Man. Where's my Monster Man at? Do not forget on the test, right to the high, left to the low, whatever way the Monster Man's tail goes. So we always say in our class, right to the high. Where's my pen? That's what we say too. Here we go. Monster Man, draw him out. There's your Monster Man. There's his tail. Right to the high. Left to the low. Whatever way the Monster Man's tail goes. High side is positive numbers, right skew, positive skew. Left side is low numbers. Look for that Monster Man tail, and Monster Man got to have that monster tooth. There's your Monster Man with his Monster Man tail. Right skewed Monster Man. So with this right here, according to the normal model, what percent, we're still zoomed in, what percent of receivers should expect to gain more than 1 standard deviation above the mean? Here's the thing. This is using, and I think Spiel have had issues with it, using the empirical rule, if I am correct. And the empirical rule we wrote out earlier, pro tip for the test that we've been saying all day, is draw out your numbers. And if you go 1 standard deviation, the context doesn't matter. According to the normal model and the empirical rule, which it should say, the answer is 16%. 68% inside, 32% total outside, 16% on either tail. And now, what would this mean? Well, for this data, we would see, and let's see if it's 16%, 16% of the total sample of 508 receivers. Imagine I tell you this. In your class, let's see, it says round to the nearest whole number. You're in a class of 300 students. About what percent of students would score 1 standard deviation above the mean? So you're in a class of 300 students. About what percent of students would score 1 standard deviation above the mean? So you're in a class, don't just think 1 standard deviation above the mean. The context, Rock knows.
It doesn't matter.
About what percent of data should be 1% above the mean? I mean, 1 standard deviation above the mean. About what percent of data should be 1 standard deviation above the mean? What percent of data should be 1 standard deviation above the mean? We'll do steer weight after this. Any ideas? About what percent of your class should score 1 standard deviation above the mean? I'll give more hints. So according to the normal model, about what percent of your class should score 1 standard deviation above the mean? These numbers here don't matter. About what percent of your class should score 1, not 34, 16%. Thank you, 100 points to Amy right there for answering. 16%, because the inner 68% has an outer 34%, 32%. And then, great job, Alyssa, right there, another 100 points. And then we see right here, did I hit that? And then 16%. Does that make sense? So 16% are expected to score 1 standard deviation above the mean. And if 16% of the class is expected to score 1 standard deviation above the mean, good to see there, a little right there, then what, let's say it's a class of 200 students, how many students are expected to score 1 standard deviation above the mean? So now you're in a class of 200 students. So remember, you said 16% are expected to score above the mean, like a probability of 16%. And now you're in a class of 200 students. How many students are expected to score above the mean? Because you're telling me 16% are expected to score above the mean. How many of the 200 would you expect? How many of the 200? You're like, well, 16% of the 200, but how many of the 200? So think about what you would do with those numbers, which is what we just did for this question. How many of the 200s? Thoughts? We just times them, right? If it's 16% of the 200, 32. So that's what we did right here is we just times 16% times the 508 receivers to find out what would we expect 16% of the 508 receivers. So just multiply. Yeah, Amy, you got it. Yep, just multiply the numbers. That's it. And that's what we did here. What do I expect 16% of the 508 receivers? Okay, what's 16% of the 508 receivers? Times them together. And then we go right here and it asks, what is 1 standard deviation above the mean? So we go to the mean. The mean is 253.756. There's the mean plus 1 standard deviation, 312.356. And there's the mean plus 1 standard deviation, round to the nearest whole number. So delete and check answer, and we got 100. Let's go check out that other steer question. All these steer questions right here. Steer question number 2. You know what? They talk about Texas A&M. I wonder sometimes, were these like designed for Texas A&M? Like, this is a Texas A&M question here. There's another IQ one. Where's the other steer question? Here it is, steer question number 2. Amy, you know what this is? We got to guess at these again. 129, 33. MyPearson, chapter 5, part 2. Steer weight percentiles. Tell me, where's the 59th percentile close to? Where's the 59th percentile close to? Where is the 59th percentile close to? Just think about it on the curve. We haven't drawn it out yet. Just think, where's the 59th percentile close to? Where would the 59th percentile be close to? Where's the 50th percentile? So think about your drawing. Once again, always draw it out. So we can think, where's the 59th percentile close to? The median. Great job, Savannah, right there. 100 points, Savannah swinging by. The median. So the 59th percentile is probably a little bit above the median. So less than 1 standard deviation. Yep, so to the, yes, Savannah, or Amy, you got it right there. More points. Yes, a little bit above it. So we're just going to take a guess here. That's what we're doing right now, is we're just guessing. So I'm going to go right here and I'm going to guess 120, 1143. There we go. 1. There we go. The 92nd percentile. This is where it gets more tricky. The 92nd percentile would be the top what percent of the data? The 92nd percentile would be the top what percent of the data? The 92nd percentile would be the top what? The top 8%. So do you see where we're at on the curve when you think the top 8% of the data? The top 8% of the data. You see where we'd be at on the curve? The top 8% would be somewhere in here, right? This is somewhere where the top 8% is at, around, and a little bit less than that, right? So I'm cheating in my head right now, doing some math. Okay, I'm thinking 1.35. 1 1/3. Okay, that's right. 100. Okay. So 1227. There's my guess. The IQR. So the IQR is going to be, oh, it has to be a weird number for that, right? Of course it does. The IQR, 75. Oh man, I'm trying to figure it out. Will you do the, yep, we'll do it right here. And that would be in the same nearest spot, Blakely. So check out the answers right here. I'm going to show the exact answers in a moment. Brian's cheating in his brain. He's cheating getting answers. What a third of that be? A tenth of that is this. So, I can usually figure this one. I can cheat. I'll cheat and do it in the calculator. 75 times 1.34. There we go. So round to the nearest whole number, 101. How many of these did we get? We got one of them. All right, we got one of them by guessing. Now let's show how to get the answers. I know a cheat number. It might be this one we got. I think we did get this one. Did we? We did get that one. Because I know a trick for that one. The IQR has a distance of 1.33 standard, 1.33 standard deviations. That's just a trick that I've known from memorizing this. Hence, I knew a math trick for that one. Let me show you what you need to do. Once again, 2.5 standard deviations. Ooh, Alec, good to see you. When doing this problem, you could get applet pictures on the test. The first thing you would do if you were using the applet is enter in the what and the what. The first thing you do when using the applet is enter in your what and your what. Mario Kart. The first thing you do when doing the applet is enter in your what and your what. What's the first thing you do? Mean and standard deviation. Mean. Good answer there. The mean and standard deviation. The mean and the median will be in the same spot, but it'll be the mean and standard deviation are paired together for symmetric normal data. So the mean and standard deviation, 1127 and 75. Now we need to say we are solving for a percentile. So we are going to find the percentile using x. We're gonna find an x, using the percentile. I misread the question. We're gonna find the x value, which is an observation in this instance, using the percentile. So it wants the 59th percentile. Percentile, it's gonna be a 5-letter word I'm looking for that starts with B, and remember this for the test. Percentile means area what to something. It's a percentile, once again, remember this for the test, it means area what to something. Great job, Alec. Area what to something. If it's a percentile, it means area what to something. 5-letter word starts with a B I'm looking for here. Percentile is area, you can look at the percentile, because I am showing percentiles, means area what to something. Man, come on, not fair. Area what to something. That's what a percentile is, below. And so that's the 59th percentile, and we said it'd be close to the median, a little bit above. We said the 92nd percentile, and kind of close. These are close-ish guess. Like, they're guesses, remember. The 92nd percentile, we said be between 1 and 2 standard deviations. Remember the picture we drew just a little while ago? We said it has to be the top 8% between here and here. And if you look at our graphic, it is between the first and second standard deviation, along with the picture we had. And then you can just guess between those numbers, 1202 and 1275, or 1277, and there's the answer. The middle 50% is to go between and do this right here, and you get Q1 and Q3, and you will need to subtract those numbers. Q1 and Q3 represent the 25th and 75th percentile. So we take the 75th percentile of this right here, we subtract Q1, and there it is right there, 101. And once again, the reason I know this is because the z-scores for the middle 50% doesn't change. The z-scores, which are on the standard normal curve, are 0.675, I believe. So if we round this to 3 decimals, 0.675 is 0.674. 5A, that should round up. But that is the z-score for it. Hence why when I took the z-score, I multiplied it by 2. And I got that right there. If you saw the math I was doing, I took the standard deviation into this. That's not a solve you would need to know how to do. That's just because I've done this problem a lot, I know it. You need to know how to look at the pictures, like the Canvas content questions, and understand what they're showing you visually. Is there any questions about this one right here? These are usually where people get stuck, but the key is knowing what the picture is showing you. The middle 50% for the standard normal, because these are z-scores right now, is contained between a z-score of negative 0.67 and positive 0.67. This is the middle 50% shown on the standard normal curve. And then ours was to put in the numbers 1127 and 75, and then we get the Q1 and the Q3, which is the range of the middle 50%. You could do it other ways, like doing the bottom 25% right there, which is the 25th percentile, and you could get the 75th percentile this way too. Any questions on this one right here? It's a very good question, I think. Knowing how to look at the pictures and understand what you're seeing is the key to these. Another one. IQs. We haven't done this one apparently. So this is basically the same question. I might do it a little bit quickly, but slow me down if you have questions. 1 hour and 3. Step 201. IQs. The 13th percentile. Round to 1 decimal. Oh man. Okay, so that's going to be like 89.2. The 96th percentile. So that's going to be 133.2. The AQR. AQR. I can do my cheat again. 16 times 1.5. We got one question right again. Yeah, I did. He took a picture, right? Good seeing him there. Yeah. I was catching all the Pokemon. So I still got my clicker on me. Where's my Pokemon clicker? Good seeing him right there. Yep. It was kind of cool. I don't know. It's people are so nice to me. They're always happy to see me. Like I was like, Brian. I'm like, hey. Sometimes I'm like confused, like, just hear my name somewhere. But no, it's really cool. So this one's the same question. I took guesses here for my knowledge of how the curve works. And the percentiles are the area below. Yeah, I think I remember. Like, was it years ago? Because I remember him as a person. Oh, that's awesome. Yeah, what do you want to cover in 320? Let's do that. We'll do that to end right here. That's a good end. Yeah, let's do that, Alyssa. You got it. And actually, it starts to coincide with 201, so really good stuff. We'll do a kind of talk through 320. 13th percentile is going to be that. I was way off. So I think 85 will just do it. Yep, that's got that one. And then the 96th percentile is this. I was closer on this one, and that would do it right there. And there's the answers. So in the 50, the middle 50 is to go between and take the difference between the two numbers. If you notice, that's a difference of 21.6. Just subtract Q1 and Q3, or Q3, Q1. Let's talk about some 320 right here. Let's do it. And thank you so much. At any point, just state the question you want done. That's how we do questions. You say, hey, can we do this? And we say, yup. Hence, I was just doing more questions because we were just in a 201 kind of thing. 201, this is the last chapter for your test we're about to talk about here. Yeah, no, let me make sure I posted things correctly. I might need to update an announcement because I think at one time I reversed it and I caused confusion. You're in the Milton Lounge? I'm over here in my office. The top button right there. There's a top button that says like find p-value using x, find x using p-value. Savannah, thank you for asking. Find p-value using x, find x using p-value. 100 points, thank you for asking. Main screen. No, I think I gotta make sure it's the same thing. Wait, a traffic engineer. I can probably find you the video on that, Blake. I think we'll end with this right here because we haven't done any 320 yet. Discord me. So the Alpine, I know I've done the Alpine one a lot. Discord, or let me know and we'll find you the video on that. Thank you for asking me. Just drop those questions all the time and I'll put them over here just so you know when we're doing it. I'm making a list right here, checking it twice and going through. So when someone says, can you do this question? I just add it to the list. So Savannah and Blakely, thank you so much for being here. Just throw it on, just say, hey Brian, do this. And then I'll throw it on the list. Even if I'm working on a question, just ask. There you go. Last 20 minutes here, gonna do some, you got it. And we'll find you the videos for the other one, or seeing when I can do more office hours. Oh, let's start talking about associations. This is chapter 6 for Stat 201. So if you're Stat 201, really good stuff too. Beagle Scouts. Okay. We have library reg class right here, which is our regression class library, reg class, regression class. RF news. That's cool. And now we're going to go here and we're going to load up data. Survey 10. Survey 10 is a survey of Stat 201 students taken in the year 2010. And we ask them questions like, what's your GPA? How many tattoos do you have? How many piercings do you have? How much do you play video games? All these things right here. Now, correlation has a specific condition to start. What is the first condition of correlation? Does anyone know? You'll know soon enough if you're in 201. What is the first condition of correlation? QQ. 100 points right there. QQ. The next condition is straight enough. The next condition is no outliers. The next condition is plot doesn't thicken. That's for regression, but we sometimes use it. Plot doesn't thicken. QQ straight enough. No outliers. Plot doesn't thicken. Now what's interesting is when you run code right here, it kind of knows this. So if I run a core matrix on the data set, it gives me what's called a correlation matrix. And you don't see gender as one of the variables. Notice how it goes straight to height and weight, and it doesn't use gender. Why? Why can't I get the correlation of gender and height? Why can't I get the correlation of gender and height? You're telling me gender is not correlated with height? What? Well, it's associated. Gender is associated. Gender is categorical, so we don't do quantitative. It's not a term we use. So we go right here, and we go in, and we can see associate. And associate, we want to associate, let's say, height with gender, and data equals survey 10. So when you look at this, you're actually getting side-by-side box plots, and side-by-side box plots can look at the association. And this is something we've also done in 201, because the data is, 201 was just doing this earlier. How would you know this data is skewed? This is last lecture, Alyssa, but what is an indication this data is skewed? Look down here. How do you have an indication this data is skewed? What would be some sort of indication that the data is skewed? The outliers. And what plot are you looking at for that? Extreme outliers. And what plot really shows that well? What plot really shows that well? 201, this is something you'd have to know too. You might call it a different name here, but that's fine. Well, and what graphic where? What graphic where? What graphic where? Yes, it is a scatter plot. It is a scatter plot. It is the quantitative or the quantile plot known as a QQ plot, known as a normal quantile plot, known as a normal probability plot, the plot that shows the probability it's normal. So this one right here shows deviations on the low side, indication to use the median. And once again, this is not correlation. Correlation is when you have two quantitative variables, and you actually do get scatter plots for this. Here is the correlation between height and weight. But we can do correlation here. The first condition literally lets you know two quantitative variables are required. If you don't have this, you're not doing correlation. You can't calculate it. It's not the same thing. But the next condition means straight enough. And probably the best way for me to let you see if it's straight enough is if we were to put a line through the data, would the line bend or need to bend to properly go through the data? And take a look at this. What do you think fits the data better? The line or the parabola? What goes through the data better? The line or the parabola? What goes through the data better? The line or the parabola? Does the data have a bend to it? And the data being the points. What would you say? Does the line go through better or the parabola go through better? It goes through better here. So don't worry, points in the chat. The parabola. There's a bend to this data. So if the line goes through the data well, and the data is well described by a line, it'll look straight enough. Data that is well described by a line will have a relationship that looks generally like this. That's super good. Data that's not well described by a line can look a lot of different ways. Like even though we can fit a line through this data, the data kind of snakes around the line. Even though we can fit a line through this data, it has some sort of exponential relationship. So even though you can put a line through it, the proper form would be something like this, and the proper form would be something like this. If we fit a parabola to this, the parabola would probably look just like the line because the parabola wouldn't add new information. Does that make sense, Alyssa, right there? Like when you look at data, you can always put a line to it. You can always just calculate, if you do two quantitative variables, the quantitative linear relationship. But when you think about, does the data follow it, the form, we call this shape, direction, or strength, direction, form, unusual features, is the form linear? The answer for the first one is yes, and the other two is no. It's got some sort of sinusoidal pattern and some sort of exponential pattern. Sinusoidal, S like sine wave, and exponential, like woo. So if it's not straight enough, consider Spearman. If it's not straight enough, consider Spearman. Spearman has a requirement though, and the requirement for Spearman is monotonic. The way to remember that is your favorite boy band, One Direction. Mono, one, direction, tonic. So with this right here, this data is mostly monotonic. If you take a look at it, it mostly goes up. I know it bends at the end and goes down, but that might be some overfitting, might just be this outlier down here, but it's mostly monotonic, as in it mostly goes up, 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 a little down. I mean, you cut that part off right there and it doesn't go up, down at all. One Direction is a good, or relationships that go in one direction can be properly modeled with a Spearman correlation. No outliers. If outliers, so if I know there. So if there are outliers, consider Spearman. Are there outliers? Things that are far away from the bivariate relationship. Are there outliers? We'll just look at the outlier issue. Are there outliers? Are there, Alyssa might have already answered. There are outliers, right? Outlier, outlier, that's extreme. Extreme outlier, 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 outliers. Another big outlier there, there's outliers. We got some outliers here. No. And plot doesn't thicken. Plot doesn't thicken basically means around the line at all times you have similar thickness. The way to check this visually is to take your data, and you'd want to look, we'll have two different relationships here. One of them looks like this, and people say to me, aha, the plot doesn't thicken, it gets thinner. And I'm like, well, that's not good either. You got this one, you got this one right here. I'll even do some weirdness like that right there. And people say to me sometimes, they say, well, this got thinner. Well, if you have less data points, it's less scatter. I do agree that's a little bit weird. Preferably, we'd like to see about the same amount of data throughout the model and the same scatter. But you really want to look for something more obvious, like this right here, where if you were to take a snapshot of the model, you'd see differing thicknesses. That's because we're going to measure this with correlation, and correlation is a measure of strength, i.e. tightness in vertical spread. And the change in spread is a difference in value of R. So the value of correlation might be something up here like 0.8 or 0.85, and then down here it might be something like 0.25. So why are we going to use one value of R for this whole graphic, like 0.60, when it's not really well described by one number? So yeah, don't do it. Minor plot thickening at the end. There is less points, bit of an outlier issue. Plot thickening is somewhat of a concern. We can run tests for that. Yeah. Now they all fail. All the tests are bad. Is it linear? No. Is it are the residuals normal? No. Is it equal spread? No. More on that with linear regression. So we were right to say how weird this is. So because there are outliers, because it is nonlinear, because we have heteroscedasticity plot thickening, we are going to use what here? Because we have issues, because it has a nonlinear bend to it, the line doesn't go so well through all the data, because there are outliers, because we see some symptoms of heteroscedasticity plot thickening, unequal spread, we are going to use what? Because of these issues, we are going to use what here? Not the log. Good guess. We could transform it. Good answer. We could transform it. That's always a possibility. You can always transform data. But we're going to use Spearman or transform and look at the transform data to see if it helps. We're going to use Spearman. Notice how we have Pearson, which is your classic correlation. Usually when people say correlation, they're talking about Pearson. And then we have Spearman. Spearman is going to be rank-based correlation. When it comes to rank-based correlation, it works differently. You could have a data set. You know what? I can actually do it right here. Watch this. In R, we have a data set of X, which will go from the vector 1, 2, 3, 10, and 50. And then we have the data set Y, 1 through 6. Yes, there we go. Notice this is not linear. This is not linear. The Spearman rank correlation is 1 though, because you actually re-express the data by going here and taking your data. I'll bear a picture. One more time. You go and re-express your data, and with the re-expression of the data, you give things ranks. And what do I mean by ranks? Well, this is the lowest x, this is the second, the third, the fourth, the fifth, and the sixth. So outliers can't be so far away because they can only be the highest numeric. And then you do the y the same, you go in here to y, and with the y, can't get my pan going, there we go. With the y, you go 1, 2, 3, 4, 5, and 6. And notice, this is a perfect rank-based correlation. So the ranks of y and x are perfectly correlated. So by doing rank-based correlation, you can't really have outliers because something can only be one rank higher than something else. You can't be extremely far away. Like if this was a billion, it would still have just the highest rank. It can't be extreme in its rank-based. It also pulls in things like heteroscedasticity because once again, you can't have this big scatter away. You can't really change and scatter much. And also what you want is it must have this, and this is a requirement, Spearman must be a what relationship? Spearman must be a what relationship? So Alyssa, good question right here, and we'll finish up the output. Spearman must be a what relationship? Let's go like this. Like lines are technically that, but then we can just Pearson with it, unless there's outliers and heteroscedasticity. It must be monotonic, must be monotonic. And so now, with this output, we would say we're going with Spearman rank-based correlation, and the rank-based correlation is 0.67469 or 0.675. I just rounded to this. And it is statistically significant because the p-value is less than 0.05. Also, we are confident that it is statistically significant because we estimate the true p-value to be contained in the interval 0 to 0.007. So I'm very, very confident that this is statistically significant, that there's a real rank-based relationship between weight and height. Like people who have a higher rank of weight, as in a higher weight, have a higher rank of height, and this is something we would not expect to see by random chance. Now we could do logs right here of it, and just re-express the data. Does that make sense, Alyssa, right there? Good questions right here. Good stuff. I think so. It does. Awesome. Well, we're going to end off. I'm going to grab some lunch. A little bit early, 3 minutes early. Time for lunch, though. Good stream. Got the lights on. Till then, bye for now, everyone. Bye. 5 hours. We've almost got these new intros ready. We're almost there.
This has been going for like 20 hours. This ends now.